Greetings everyone, thank you very much for joining this presentation. My name is Ioannis Kafetzis and I'm going to present to you our work about efficient computer-aided design of emulation circuits for nonlinear polynomial systems. First of all, electrical circuits of course play a central role in physics and engineering in general, and therefore there have been a lot of computer tools developed around them. Most of them take a circuit as input and they either simulate its dynamics or try to extract a mathematical model for its function. And this is one part that has been studied. Additionally, especially in the field of chaos, a lot of works introducing novel chaotic systems also design circuit emulators for the systems that they develop, and this is mostly to prove as proof of feasibility that actually the developed systems can produce chaos in the real world. And combining the two things above, we have our goal. We wanted to create an application where the user gives a set of nonlinear equations, polynomial in our case, and the system automatically generates a system that emulates the given nonlinear equations. And we used simple analog units actually, starting with the inverting operational amplifier that takes a V input, and there are two resistances, R1 and R2, and if those are selected to be equal, then the output is actually minus the input. And this is one of the key components. The second is the inverting summing operator, again based on operational amplifier, where you can see that it takes, in this case 2, but it can take multiple signals as input, in this case V1 and V2, and what it outputs is actually the integral as described in this equation. So with this one we can actually simulate the integration process. And finally, in order to generate products or powers, we used an analog multiplier, and the output is this one, as described in the equation. And what's really important to observe here is that if we don't want any of the x1, x2, x3 or y1 or y2, we can just connect it to a ground so that it turns to 0. And it's also worth mentioning that we can generate any sign required. So if we want a positive product, we connect them to x1 and y1. Whereas if we want a negative product, we can connect signals to x1 and y2, for example. And this is something that we use so that we generate products with required signs, thus requiring the minimum amount of inverting amplifiers. And what we also built was an application and an interface so that we wanted to make this tool easy to use and without requiring any programming knowledge. And it's Python based so that it can be open source and everyone can basically run them. And what it does is it asks for the user to input the number of variables or the number of equations. Subsequently, the user adds the variable names and the equations. And we actually made this into a web application that is currently online accessible, and it looks like this. So you can see in the first field the user can input the number of equations. Subsequently, based on the number of equations or the number of variables, the respective amount of variable names is required, and also the number of equations. And what better way to investigate this by considering the example of a dynamical system. And we can see first of all that the input would look like this. We have 4 equations, so the number of equations is 4, variable names x, y, z and w, and we input in every one of the equation fields the right hand side of the equation. But what better way to actually investigate this than running the example in real time. So we input the number of equations, which is 4, and you can see that automatically the 4 fields appear, and we give the variable names, which will be x, y, z and w. And for the first equation we had that it is equal to x, z, w, and for the last equation, that was the larger one, was minus 1,05 times w plus 7 times x squared. This is the standard Python notation where 2 stars indicate exponentiation, minus 1,9 times y squared plus 13.7 times x times y plus 17.9 times x times z plus 0,115. And then we can see that clicking here the equations appear so that we can verify that the inputs are correctly, and pressing the create equation plots we start and we see the figures. The first figure has to do with the generation of all powers. The powers required in the we only require powers in the last equation in this case, and it's x squared and y squared. Observe that the sign of x squared is positive, and because we have an inverting integrator, we need actually minus x squared, and this is why we consider that we have the signals x available and connect them to x1 and y2, and from the formula we actually get minus x squared. So we have not only created x squared, but we don't need to invert it because we have achieved the appropriate sign. Similarly, y squared is actually with a minus, so we need a positive output here, and this is why the y signals are connected to x1 and y1. Let's now consider what we expect from the first three equations, and we see that it's simply y, but since the coefficient is 1, we would need to actually get minus y as a signal to pass it through the integrator, and this is exactly what we see. We see that minus y gets passed to the integrator, resulting in the variable x, because it's the first equation, and this is the circuit, the inverting operational amplifier, that describes the generation of the minus y signal required. Similarly, for the second equation, we have minus z as an input to the integrator, outputting y, where minus z is generated by adding by passing z through an inverting operational amplifier. Same holds for the third equation, where minus w is the input to the integrator, and minus w is generated via w through an inverting one. And the last equation, and most important, we can see it here. This is the integrator that actually generates signal w, and we see that we have minus x times y and minus x times z. Minuses again are generated based on coefficients, and we can see that they get achieved using the multipliers, and since we want minus x in both cases connected to x1, and z and y respectively are connected to y2, so that we get the negative output, and the resistances here get tuned based on our capacitor, so the capacity of our capacitor, and also the integration constant, that in our case is 10 to the minus 4 as a design parameter. And we can see that every one of the terms gets multiplied with the respective coefficient. We also have an input with the required sign, and every one of them get integrated and result into the output w. This way we have managed to obtain a system, that a complete analog circuit that emulates our given system. And this is actually once again the system, and we see the equations as discussed. And to conclude this presentation, we actually developed a method that, given equation of a nonlinear system, designs a circuit emulated for it automatically, and it's also the power computations happens in such a way that the minimum number of operations are required. We implemented this actually as a proof of concept into a web application that is available online, and this method works for polynomial systems, which is a very general category of dynamical systems. And moving forward, we plan to implement even more functions, find ways to use sinusoid signals, absolute values, hyperbolic functions, so on and so forth. We also want to make this application publicly available, and publicly available in both in terms of the web application that requires no programming, and also the source code if someone wants to further contribute to its development. And we also plan to evaluate using the proposed application in teaching and see if and how much it helps students, for example in the Department of Physics, with their studies. And finally, we also want to combine this with modeling methods to create emulators from real-world data. So given a real-world time series, create a model that actually fits the time series. Through the model, generate a circuit emulator, actually implement the circuit, and see if with this circuit we can get close to the original data. With this, I would like to thank you for the presentation. If there are any questions, feel free to reach out either after the presentation or via email. And once again, thank you very, very much for your attention.